Hi, I am Dr. Harikrishna Mulam, Associate Professor, Department of EAE, VNR VIGNANA JYOTHI. Today, we will see one more problem related to time response analysis. This is the problem. The unity feedback system. Unity feedback means we can write feedback system, feedback transfer function is written as H of S. As it is unity feedback system, H of S is 1. Unity feedback system, therefore H of S is 1. And such a system is characterized by open loop transfer function G of S is equal to K by S into S plus 10. Therefore, open loop transfer function G of S is equal to K by S into S plus 10. Okay, so this is the information that is given, and what is that we need to find is we need to find this K value. You need to find this K value so that the damping ratio of the system is 0.5. Damping ratio means zeta. Zeta should be 0.5. After finding this K value, you should also find settling time, which is represented by Ts, peak overshoot, represented by percentage MP, and time to peak overshoot, which is represented by peak time. Okay, when the input is unit step input. Here the input that is considered is unit step input. Input is written as R of t. As it is unit step input, mathematically it is written as 1. Okay. Now, first of all, in a closed loop system, you are supposed to find the closed loop transfer function of the system. If you find the closed loop transfer function of the system, then you can get information about zeta as well as omega n from that closed loop transfer function. And if you know these two parameters, that is zeta and omega n, you can find all time domain specifications like settling time, peak time, overshoot, even rise time. Okay, all the time domain specifications can be found. Therefore, first of all, let us find the transfer function of the system. Transfer function of a closed loop control system in terms of open loop transfer function and feedback transfer function is given by G of S by 1 plus G of S H of S. Okay, therefore that is equal to G of S is K by S into S plus 10. Therefore, S into S is S square plus S into 10 is 10S whole divided by 1 plus G of S is once again K by S square plus 10S into H of S is 1. Therefore, if you simplify this expression, the denominator of numerator and the denominator of denominator is same. Therefore, they get cancelled. And finally, you will get a transfer function of K by S square plus 10S plus K. Okay. So, this is the transfer function of the given feedback system or closed loop control system. Then, in order to find all these time domain specifications, you need to get the information about zeta and omega n, but already in the problem, they have given zeta as 0.5. Therefore, to find omega n, always compare the transfer function that you have come across in the problem with the standard way of representing the second order closed loop system transfer function. We have already discussed it several times. The standard way of representing the transfer function of closed loop second order system is omega n square by s square plus 2 zeta omega n s plus omega n square. So if you compare the denominator polynomial of our transfer function with the denominator polynomial of the standard transfer function, we can write, see, this k is equal to omega n square. K is equal to omega n square. Okay. Therefore, omega n is equal to root of k. Okay. Then similarly, if you compare this term with this term, okay, we can write 10 is equal to 2 zeta omega n. 2 zeta omega n. Therefore, omega n is equal to 10 by 2 into zeta. Zeta value is given as 0.5. So 0.5. So 2 into 0.5 is 1. 10 by 1 is 10. So omega n in this system is 10 radians per second. 10 radians per second. So we have found omega n, which is 10 radians per second, and the zeta value is already given, but we got the relation between omega n and k. So k is equal to omega n square. Therefore, we are supposed to find k value, right? K is equal to omega n square, whereas omega n is 10. Therefore, 10 square, k value will be 100. K value will be 100. Okay. So in this problem, in order to have a damping ratio of 0.5, your k value, the gain, should be equal to 100. Now, once you got this omega n value, which is 10 radians per second, and once you know zeta value, you can find all the time domain specifications. So first, we were asked to find settling time. Settling time is given by 4 by zeta omega n when you consider the steady state error as 2% error. Okay. Or it is given by 3 by zeta omega n if you consider 5% steady state error. 5% steady state error. Therefore, settling time Ts is equal to 4 by zeta is 0.5 and omega n is equal to 10. That is equal to 4 by 5, which is equal to 0.8 seconds. Similarly, here for 5% steady state error, the settling time is 3 by 0.5 into omega n is 10 radian per second. That is equal to 3 by 0.5 into 10 is 5. That is equal to 0.6 seconds. So if you consider the steady state error as 5%, it takes settling time is 0.6 seconds. If you consider the steady state error as 2%, the settling time is 0.8 seconds. Then let us find peak overshoot. This peak overshoot. Peak overshoot or percentage peak overshoot is given by the formula e power minus pi zeta by square root of 1 minus zeta square into 100. That is equal to e power minus pi. Pi value is 22 by 7 or 3.14. Okay. Into zeta is 0.5 divided by square root of 1 minus zeta square. 0.5 whole square is 0.25 into 100. If you solve this, if you find the value for this expression, you will get it as 16.3%. Okay. So the overshoot that is present in this system is 16.3%, which indicates that there is a deviation of 16.3% of the final value, okay, in the output during its first peak. Now we have found settling time, we have found percentage overshoot. Let us find peak time and rise time. Peak time formula is given by pi by omega d. Omega d is the damped natural frequency of the system. That can be written as pi by omega d is written as omega n square root of 1 minus zeta square. And we know omega n value, it is equal to 10 radians per second. Zeta value is equal to 0.5. Therefore, if you find omega d, okay, it is equal to omega n 10 into square root of 1 minus zeta square, that is 1 minus 0.25. Then if you substitute those values, peak time is equal to pi by 10 into square root of 1 minus 0.25. If you solve this expression, you will get it as 0.363 seconds. The peak time is equal to 0.363 seconds in this system. Similarly, though it is not asked in the problem, I would like to find one more parameter among time domain specifications, that is rise time. Rise time is given by the formula pi minus theta by omega d. That is equal to pi minus theta by omega d is omega n square root of 1 minus zeta square. Here you need to find the value for this theta. The theta expression is given as tan inverse square root of 1 minus zeta square by zeta. That is equal to tan inverse of square root of 1 minus zeta square is equal to 0.25 divided by zeta is equal to 0.5. That is equal to tan inverse square root of 0.75 by 0.5, which is equal to tan inverse of square root of 0.75 is roughly 0.866 divided by 0.5, which we will get approximately as 60 degrees. But the theta should be considered in terms of radians in this formula for rise time. Therefore, this 60 degrees should be converted into radians. How to convert it into radians? 60 degrees, and it should be multiplied by pi by 180 degrees. So 63 is 180. So pi by 3. Pi by 3 radians is the value of this theta. Therefore, if you find the rise time is equal to pi minus theta is pi by 3 radians whole divided by 10 square root of 1 minus 0.25. That is equal to pi minus pi by 3 is 3 pi minus pi by 3 whole divided by 0.866. That is equal to 2 pi by 3 whole divided by 0.866, which is equal to 0.242 seconds. So this is the rise time, this is the peak time, and settling time we got it as 0.6 seconds for 5% error, 0.8 seconds for 2% error, and overshoot is 16.3%. We can have a look at how the response appears. Okay, so for a unit step input, this is unit step input. Okay, and your second order system response looks something like this. So a rise time is the time taken for the response to reach 100% of the final value for the first time. Therefore, this rise time is equal to 0.242 seconds. Whereas peak time is the time taken by the response to reach the peak value for the very first time. And we got that peak time as 0.363 seconds. 0.363 seconds. Then settling time, which is found in the steady state response. Okay, settling time. The settling time, we got it as 0.6 seconds if the error is 5%. And the settling time, we got it as 0.8 seconds if the steady state error is considered to be 2%. And this is the overshoot. Which is the deviation from the desired value. Okay, this overshoot percentage in this system is 16.3%. Okay, like that you can find the time domain specifications of the system once you get zeta and omega n value. To get zeta and omega n values, first of all, you need to find the transfer function of the system. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.